All right. Let's get going with today's material. So today we're covering the last chapter that we'll be doing a lot with waves, and we'll be covering today sound waves. Sound waves. Intuition for what we're covering today is now we're covering longitudinal waves. Chapter 15, we were really focused on transverse waves. Chapter 16, now we're going to be really focused on longitudinal waves. Because if you think about your broadest definition of sound, sound is going to be defined as a longitudinal wave in some medium, something to that effect.
In some medium.
In some medium. You can't have sound outside of some medium because sound is creating pressure differences. Pressure differences in what?
Oh, I see.
So if you're standing on the surface of the moon, you take off your spacesuit and you scream, you're not going to hear anything. There's no atmosphere. There's no air molecules for you to vibrate. Now, it doesn't mean that there's no sound on the moon. When you stomp, it makes a sound just in the earth. It sends a longitudinal wave through the earth, using a broad definition of sound. So just because you can't hear it doesn't mean it's not sound.
Yeah.
And so, for example, dogs are said to be able to hear earthquakes. Not sure how, but supposedly it's a thing.
Have they
Don't touch that.
proven on like the scale how much the human can hear?
Humans can roughly hear from 20 to 20,000 hertz,
Okay.
roughly. As a general rule, you lose a higher frequency hearing with age, and then people vary drastically. So like I know that my ears personally, I can hear higher frequencies better than a lot of people I'm just typically around. Like I can, old tube TVs, you might not remember them. I could always hear one when it was on.
Oh yeah, those are so nice.
So chances are you and I don't have the same hearing. So one thing, maybe I can hear more high frequencies than you can hear. You can probably hear more low frequencies than I can hear. And the second thing that goes into your hearing is how loud things sound. And so the intensity of a wave might not have the same effect that it did before. So people who expose themselves to really loud noises for an extended period of time actually recalibrate their ears. And so now they actually can't hear the quiet sounds that they used to be able to hear.
Really?
Yeah. Now that has nothing to do with the frequency. That has to do with how intense the actual sound is. If I were to take a paperclip and drop it on the floor, you're not going to hear it. Or a pushpin, I mean. If you drop it on the floor, you're not going to hear it. It doesn't mean it didn't produce a sound. It doesn't mean the sound it produced was in a frequency you couldn't hear. It just wasn't an intense enough of a sound.
That makes sense.
And so people who damage their hearing somehow, a common way is by listening to loud noises over and over again. We say damage their hearing just because it's no longer normal. What they do is they recalibrate their ears for loud noises. Makes loud, quieter noises they now can't hear like they used to.
That makes sense.
Does that mean it could be recalibrated?
I don't know. If it's permanently recalibrated, I'm not sure if you could force it to go back the other direction. I don't know. It's pretty amazing what can sometimes happen. So, but they probably have to do something pretty drastic. So there's notions of what are called quiet rooms, or I can't remember exactly what they're called. But they're rooms that basically are designed to completely eat up sound. So even the walls, there's like a spongy material, but it comes out in cones. So the walls, there's like cones that come out like this.
Mm-hmm.
To eat up the sound waves, so they'll vibrate slowly and nothing will bounce back out. And so, even being in one, you listen to people who have been in one before talk about it, they say it's really weird because it's like, you're so used to just regular echoing. And so people who are in this room, they said their ears recalibrate in the short term, and they suddenly can hear lots of things, like gets to a point where they can actually hear their heartbeat, stuff like that. So, maybe if you spent a ton of time in a room like that, you could get your ears to recalibrate. I have no clue. I wouldn't be surprised if it was possible. To permanently recalibrate.
Yeah.
Anyways, so that's what we're talking about today, sound. And we're talking about sound in a more general way. We're talking about it as a longitudinal wave through some medium. It's not necessarily something that a human being can hear. Now, with sound waves, we're still going to model them with the same equation that we used for transverse waves. We can still use our regular old equation, yxt is equal to a times cosine of kx minus omega t. We just have to keep in mind that now y is going back and forth in the x direction.
So y is the x, basically?
Yeah, in this case, our little y displacements are in the x direction.
So why not just say x?
Because it's not giving you your x coordinate, it's giving you how much that particular atom shifted. So we have a bunch of air molecules in the room jiggling, right?
Yeah.
And if y, so let's say that this is, here's our x-axis, right? And let's say that this is x10, right?
Okay.
And we'll say that this is what the air molecules look like at time t equal to 0. Let's say that 1 second later, this molecule now moves, so it's right there. You with me?
Mm-hmm.
So this one moved forward a little bit. This one just moves forward a little bit, so it's right here at some future time. So now at t equal to 1, it looks like this. And so it moved this distance. Right?
Yeah, but wouldn't it?
Let's say that this
also be
distance
down?
is 1/2. That means y at 10 with 1 second later is equal to 1/2. It's not giving you the x coordinate. The x coordinate of that thing is now x1/2. Its jiggle is just 1/2. Y is still giving you just how much it shifted from its equilibrium position. In our rope, that happened to also be its x coordinate. Or it happened to also be its y coordinate. Because how much you shifted up was your y coordinate.
Yeah.
Now how much you shifted over, it's not your x coordinate, it's not your y coordinate. It's some little change in the x direction.
And we're calling that change y?
Yeah, we're still going to call it y. Everything behaves the same.
Okay.
Rather than simple harmonic motion this way, we have simple harmonic motion this way.
Okay.
But it's still plain old simple harmonic motion. Does that make sense?
Yes.
Now this is one way that we can talk about a sound wave moving through some medium. We can talk about it as it's the individual atom shifting up and down that's moving. But the other way that we can talk about it is we can talk about it in terms of pressure differences.
Okay.
And so let's try and draw a picture for that again. Go back to some old picture I have to try and make intuition for how a sound wave is a pressure difference. Because ultimately, that's what your ear is detecting is pressure differences. And so what's physically happening, try and draw a more realistic picture this time than what I did last time, but it's still way oversimplified. Maybe we can just look at 5 atoms. I don't know if we'll need more than that. So here's 5 atoms, and we're going to look at these 5 atoms over some small time intervals, right?
Yes.
Now, my mouth is right here, and I start talking. And talking is essentially I'm pushing on air.
Pushing on air. Okay.
Yeah, that's what you essentially do in talking. You push the air. Or think about your speaker. What does your speaker do? Well, that was different. It's not.
I get
Okay.
the question.
Think about a speaker. It's pushing on the air. So that's what it's ultimately doing, just pushing air. So I'm talking, and what that's enabling me to do is keep pushing this atom every time it gets close enough to me. Right?
Yes.
So I start pushing this atom, so after some second, this atom is now in motion. So it's right there. This one's still right here. This one's still right here. This one's still right here. This one's still right here, right?
Mm-hmm.
And some moment later, it finally collides with that. So now you have some collision. This one's still right here. This one's still right here. This one's still right here, right?
Yeah.
And now this atom's going to start bouncing back towards me. And so it's going to start bouncing away. This one's going to start moving in that direction. This one's still in the same place. This one's still in the same place. This one's still in the same place. Right?
Mm-hmm.
And then this one, it's going to take too long. I'm trying to do it over small enough intervals. I can show you 2 concepts at the same time, but it's not going to work.
Okay.
We're going to have to draw too many. So, shoot. So, you're going to have to keep it even simpler. This picture's lying, but it gives you the intuition. So back once again, we have our atoms. Here's one, here's one, here's one, here's one, here's one. I start talking, which pushes that one. So then it collides it with this one. This one's still where it is. This one's still where it is. This one's still where it is.
This one now bounces back and hits that one forward. So this one bounces back here, hits this one forward over here. I'm still talking, so I push that one forward again, so it goes forward. This one bounces back, so now it's over here. This one bounces forward, so now it's over here. And this one still hasn't moved yet. Right?
Okay.
And we could continue this process. After a while, what will the process look like? I'll have maybe the one that came back to me, then we'll have 2 bunched up, big gap, 2 bunched up, big gap, 2 bunched up, big gap, etc. However far the sound wave's gone, then we'll go back to atoms that aren't pushed up or separated, like that, right? However far my sound wave's gone so far.
Mm-hmm.
And so you see it says low pressure, low pressure. Where you have a lot of atoms is high pressure. So here's a high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. So it's a bunch of pressure differences. If I were to model the pressure now at each point, we have, here it's normal, but then we have low pressure, then we have high pressure, then low pressure, then high pressure, then low pressure, high pressure, low pressure, etc. And we create a
So
sinusoidal
how
wave.
you graph the wave is like a wave.
Yeah, when you graph the pressure differences, it's still going to give you a sinusoidal wave.
Okay.
So there's 2 ways that we can talk about a sound wave. We can talk about it the same way we were talking about these waves, where we can talk about its displacement, how much it's jiggled from equilibrium, a particular atom, how far it's gone from equilibrium at some position at some time, right? But we can also talk about the pressure of the wave at some position at some time, and what that equals. And we're going to come up with the equation to figure out what this is.
Okay.
Because with sound waves, it turns out it's often far more convenient to talk about it as a pressure wave rather than a displacement wave.
So why is your example lying?
Because it's not just atoms, 2 atoms moving back and forth like this.
Yeah.
It's more like this. We have the atoms all equally separated. And then once I start talking and send a sound wave through it, then it'll be more like these ones are a little bit more compressed together up to some maximum compression, and then they space out more and more. And then back to getting higher and higher density, and then space out more and more. So it looks more like that, rather than just 2 atoms. They bunch up and spread out, bunch up and spread out. It's not just 2 atoms bouncing back and forth really quick.
Yeah.
That's the difference. Okay. And your book has a bunch of much better pictures than what I can quickly draw on the whiteboard to help get this intuition down.
Okay.
Anyways, so let's start coming up now with representing this wave as a pressure wave. We know how to represent it as a displacement wave. Now how can we represent it as a pressure wave? You with me?
Yes, but wouldn't it just be like a sinusoidal wave?
We suspect it will be some sort of sinusoidal wave. But now we'll derive the equation and see that our intuition is correct.
Okay.
Okay. So for this example, we're going to think about some sort of pressure wave going through some tube. So here's some tube. And this is going to think about it as a spherical tube. I don't want to try and draw it 3-dimensional, but like a pipe. So this is some pipe.
Okay.
And this right here is a circle with a cross-sectional area. Maybe I'll first draw really quick 3-dimensional, then we'll go to 2-dimensional to fill it out. So I'm talking about something like this. We've got some cylinder. Like that, except for now I'm going to draw 2 dimensionals. And the surface area here we're going to call S, the cross-sectional area. Okay, so redrawing the same picture. Here's our pipe. This is S inside of our pipe. Now, so we're looking at the air inside this pipe. Let's say that the air is initially like some slice of the pipe. Air inside some cylinder. So I grab like some cylinder out of thin air right here, and I'm just throwing it right here, and we're going to send a sound wave through it. Some little piece. So here's that.
The rest of it is like void?
No, the rest of it, around it, you can just think about regular atmosphere. Or you can think about it as a pipe.
I'm saying inside the pipe, you're just sticking.
There's air molecules in there.
But what about that one little area you said?
Right here in this area. So I'm going to say where we're
Oh,
starting
I
this,
see.
we're going to call x. That's this x coordinate. And then where we're ending this, I'm going to call x plus delta x. So some little piece of air right there on the whiteboard, right?
Okay.
And I'm going to send now a sound wave through that air. So I send the sound wave through it,
Which is going to cause the air to wiggle back and forth like this, right?
Yes.
So it's going to cause the air to wiggle back and forth.
And so this air right here is going to wiggle forward to some position. It's going to go forward by some position, we'll call it y1. So when I send a sound wave through this air, all the atoms that were right here jiggle forward that far.
So they're going to go forward, back, whatever.
Okay.
It doesn't matter how much.
But some distance y1. Maybe y1's actually in the other direction.
Why? Oh, I see.
Because they could be bouncing off the air and now coming back, right?
Yeah.
So some direction we don't know. And y2, the air molecules that were right here are going to be they're going to move some distance y2. So remember y2 is, maybe I should draw it like this. y2 is this distance right here, y1 is this distance right here. They're not coordinates, they're distances, right?
Oh, I see.
And so just come back and plug it into this equation.
y1, just to make sure we're very clear, y1 is equal to y when you plug in our x coordinate here and whatever time we're talking about, time t.
Okay.
And y2 is
However much the atoms jiggled at this position. And this position was y, this position was y at x plus delta x, and then at some other time, or at the same time t.
So they're both at the same time. These ones shifted that much, those ones shifted however much they shifted. Using just our regular displacement equation. That's what y gives us. Y is this equation right here.
Yes.
And that just gives me the displacement, right?
How did your y2 move more than your y1?
Maybe it did, maybe it didn't. It's overall displacement. Remember, the atoms are just jiggling back and forth. And maybe this one happens to be at the peak of its jiggle, while this one already reached its peak and now it's bouncing back.
Oh, I see. Okay.
Right? So, don't read too much into my picture. The point is y1 and y2 could very much be different. There's no reason that I picked 2 points where they're perfectly in sync.
Yeah.
Right? Okay. So, this is after some splits,
This is at time t, what these displacement equations give us.
good so far?
Yeah.
Okay, so now, maybe before we go too far down this rabbit hole, we need to do a throwback back to one of our old equations. Bulk modulus, this is coming from chapter
13, I think.
Our bulk modulus was the negative of our change in pressure over our fractional change in volume.
Oh, yes. Okay.
And so a bulk modulus was kind of a measure of a material's resistance to compress.
Yes.
Maybe write it one more way to help appeal to the intuition. The exact same equation we could write as b is just some constant, times our fractional change in volume produces a negative fractional change in pressure.
Why is it negative?
If our volume goes up, our pressure goes down. If our volume goes down, our pressure goes up.
Okay.
So when we have a negative change in volume, we have a positive change in pressure. When we have a positive change in volume, we have a negative change in pressure.
Okay.
Oh, I might have done a throwback to that equation too soon. Oops. We'll be using that fact no matter what here in a bit, anyways. But we probably don't need that for what we were doing.
Okay.
Sorry. Okay, anyways, back to this. So, the quantity that we're going to look at is I'm going to look at, well, first we'll just calculate some quantities. So let's see what the initial volume of our air was. The initial volume of the air was our surface area times this distance, right?
Yes.
It's the volume of that cylinder.
Mm-hmm.
What's this distance on our cylinder? What's that distance?
S times your
What is this distance? Just asking the distance, not the volume.
Delta x.
It's just delta x. This distance right here is just delta x. So the volume that the air initially occupied was
S times delta x.
S times delta x. Perfect. Okay, now our volume as some future. Our volume after we have the shift.
Isn't it the same?
No, now it's this distance.
What would you call that? Delta x1?
No, we're going to calculate that distance. We know what this distance is. This is y2. Right?
Oh, I see.
This distance is delta x. This distance is y1. So it's delta x plus y2 gets us this, subtract y1.
Okay.
So volume 1 is S times, we have y2 minus y1 plus delta x. You okay with me writing it in that order? All times S. So our change in volume now, our change in volume, delta V, what's our change in volume?
V1 minus V0.
Right? Which is going to be S times y2 minus y1. Right? Because we're going to subtract an S times delta x from this. Remember, this is a times, this isn't a function.
Yeah, I get how you got rid of your delta x, but why not get rid of the s? Or am I just confused?
You can't.
You
just
can't.
factor it.
Multiply this out, and then subtract that. Then factor out your s again.
Oh. Okay, I see.
Okay, so here's our delta v. Right?
Yes.
So now we're going to look at what is delta v over v.
Well, what's your v?
So our delta v over v, that's just our initial volume. Change of volume over initial volume, sorry, so v naught in our case. I'm just writing it that way. Our change of volume over our initial volume, then, is equal to
y2 minus y1.
s times y2 minus y1.
You can get rid of the s.
Yeah, I just don't want to do too much in one go. All over s times delta x, right? S's cancel out, and we're left with y2 minus y1 all over delta x. With me so far? Now, this quantity, if you think back to calculus, this almost looks like what? That's a comma right there. What does that almost look like?
Kind of like a limit or something?
Almost like a derivative, right? If we go back to our definition of a derivative in terms of f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x.
Okay.
You with me?
Yes.
Now, you haven't come across this before, but our definition for a partial derivative, the partial derivative now of y with respect to x, we'll say, would be the limit I don't know that I want to write it out that way. Let's for a second just take a limit now on both sides on this, and then I'll plug it in and we'll go back to it. So I know that delta v over v naught is equal to this thing, right?
Yes.
Now I'm going to take the limit as delta x goes to 0 of both sides.
As delta x goes to 0? Okay.
So over here, we get dv over v naught. As delta x goes to 0, our change in v just becomes an infinitesimal.
Yes.
And then v naught still constant. And that's equal to, now we take the limit of this as delta x goes to 0. Now notice that this would be a regular old derivative if we didn't have these t's here.
Yes.
If we didn't have the t's here, then this would just be the derivative of y with respect to x.
Why don't you just say define x as x comma t?
You can't.
X comma t isn't a mathematical expression.
Then what is
I can define x as x plus t. Look, if I tell you that 7 is equal to 2 comma 5, what does that mean? It doesn't mean anything. That's not a mathematical expression. So you can't just substitute it. That's what we mean. So no, you can't do that. But notice that the t here and the t here are the exact same.
Mm-hmm.
Yes.
So the t isn't changing from point to point. Only the x is changing.
Okay.
This function, you're plugging in the same t to both those. This isn't a different t from this t. Those t's are identical.
Don't you plug in the same x too? And just the delta x?
Yeah, but in the x position, you're plugging in an x plus delta x here. Here, you're just plugging in an x.
Oh, yeah.
Right? So you're plugging in different values on the left-hand side. You're plugging in the exact same value on the right-hand side. So the right-hand side value is, even though time isn't a constant, right here, if we treat it like a constant, then the only way that it's varying is x to x plus delta x, which is what we mean by partial derivative. So what we mean by partial derivative now is the limit of something like this is delta x goes to 0, where the other constants aren't changing. Sorry, where the other variables aren't changing, and so you can treat them like constants. So since t is the same here and here, we take the derivative of this as delta x goes to 0. That's exactly what partial derivative is. So this is the partial derivative of y with respect to x. You follow that?
Yes.
Yeah.
Okay, so now we know what the partial derivative of y with respect to x is, right? There's y. When we take the partial derivative of y with respect to x, what do we get?
With respect to x?
Negative or k. A sine of the middle stuff.
Good. So we took the partial derivative of that. So now our change in volume, our fractional change in volume is equal to this value right here. You with me?
Yes.
Now coming back to this equation, notice that if we were to take the derivative of both sides of this, or take the limit as our delta v and delta p go to 0, then we would get b times dv over b is equal to negative, and then our instantaneous change in pressure.
What is that?
That is what we're trying to calculate. That we're looking for a function, pxt, whatever that is. That's what we're looking for a wave, pxt. So we don't know what the instantaneous change of pressure is, but notice as our volume gets infinitesimally small, then it's going to give us an instantaneous change in pressure here.
Yeah, that makes sense.
Okay, so that's a function that we're ultimately looking for. The same way that this was your instantaneous change in displacement, we were looking for an instantaneous change in pressure function.
Okay.
So our instantaneous change in pressure, the negative of it, is equal to dv over v times the bulk modulus b.
And what is b?
A constant. Depends on your material. It's really low for the air in this room. The air in this room is really easy to compress.
So it's how you
It's really high for water. It's really hard to compress water.
Yeah, that makes sense.
And the harder it is to compress a material, the faster the air waves jiggle through it. It's like if I shift a water wave, a water atom a little bit, it interacts with its neighbors much quicker. That interaction is sent much quicker.
So sound through water moves faster than in air?
Yes. And sound through steel moves faster than it does in air. Sound moves, relative to other materials, sound moves slow through air. Fast through other materials.
Interesting. That's weird.
Not really, because it's like it's jiggling it. What should you be able to detect better? If I'm jiggling this air that you and I are on, or if I'm jiggling the floor that you and I are on?
The floor.
Because it has a higher bulk modulus.
Okay. Yeah, that makes sense.
So it's intuitive, we just don't think about sounds traveling through other materials as much as we think about sound traveling through air. But yeah, disturbing the air and you feeling that disturbance, it's much harder to feel than if I disturb water that you're in or something like that. It's communicated much slower.
Yeah, that makes sense.
Okay, so anyway, so we got dVV is equal to negative rho, or negative P times our, we've got that equation. I keep saying it wrong, but I think you understand what I'm trying to say,
Yeah.
right? Did I write that equation correctly? Oh, no. When we move this, no, we did that right. Maybe it's fine. I think I'm overthinking it.
Okay.
Okay, so anyways, looking at this equation now we know what dV over V is. We calculated that right here.
Yes.
So dV over V is this right here, this wave.
Times speed, but what does that change about the equation?
So negative Pxt, or instantaneous change of pressure, is equal to B times dV over V. And so plug that in right here. We got our negative, I'm going to write that first. So then we had B Ka sine of Kx minus omega t. We can get rid of the negatives on both sides, and finally we get our pressure equation. Pxt is equal to Bka sine of Kx minus omega t. And so now we have it.
What?
Where did I lose you?
Isn't that basically the same equation though?
This and this?
Yes.
Notice that they have different amplitudes.
B is an amplitude?
It's a constant. B is a constant, K is a constant, A is a constant. But this A is the same as that A.
Okay.
So they have different amplitudes, which
Why would
makes
they
sense.
have different amplitudes if they're all moving in the same direction?
This is a pressure amplitude. This is measuring the pressure at a point.
Oh, and it goes.
This is measuring in pascals, this is measuring in meters. There's no reason for those to be the same number. Why would it be that if you displace 1 meter, you create a pressure difference necessarily of 1 pascal?
Yeah, that would make sense.
Right, and there's a huge difference between me displacing the air in this room by 1 meter to produce a sound wave, versus if we were inside water and I displace the water by 1 meter.
Yes.
The medium also makes a huge difference, which is where the B comes in.
So the B is the medium.
The B comes from your medium, that's your bulk modulus.
Okay.
Your A, that's your amplitude here, because obviously the more I shift the air, the more pressure difference there's going to be.
Yes.
So that's where this A comes in. And then this K comes from this K right here.
And what's that K right there? Wave number?
That K right there is the wave number. Can we connect that with our intuition? I mean, it's related to the frequency. Best way for me to say that is high frequency waves create bigger pressure amplitudes than low frequency waves. So even if your wave has the same amplitude and you're in the same medium, if I drastically increase the frequency, then that's going to also increase the pressure.
That makes
Why do
sense.
you mean increase the pressure? Like the distance between them? The low and high pressures? Or the density of the pressure?
So when I move my hand back and forth like this, it creates some sort of sound wave through the medium, right? Now I keep my amplitude the same, but now I do it like this. It's going to create higher pressure differences. if I were to model my pressure, before my pressures would have been like this. Now, if I shift my hand back and forth even faster, my pressure differences are going to be more like this. Well, they'll also be closer together because K also shows up right here. But the reason, part of it showing right there is causing the pressures to be shifted more.
Okay.
The air becomes more tightly compact and therefore even more decompact right next to it. A high frequency wave can compress the air more than a low frequency wave. So remember, this is measuring how compressed the air is, how much pressure there is. This is measuring how much the air has shifted.
Not necessarily the air, but the medium, right?
Yeah.
Okay.
When you're talking about actual sound through air, then this is how much the air atom has jiggled. This one is how compact the air atoms are, or spread out they are. And
they
same with
both-
if it's in water or
And they
whatever.
both make the same sort of wave when you measure them?
They both make a similar wave. This one has a different amplitude, we noticed. Now, the other thing that we noticed is this is a cosine wave, this is a sine wave.
So it's shifted.
So it's shifted. So let's try and connect that shift by roughly drawing, I don't know if I'm going to be able to make this make sense with the picture. We'll see where it goes. So when we're looking at this one, a cosine wave, then that one is going to look like this. It starts out up here, and that one's going to come like this. Right? The pressure then is going to be modeled like this. Let me plot some points in here so I don't get way off track. It's going to be a phase shift version of it. Maybe that's enough. And maybe a little bit dotted lines for this one to help make it more clear. So here's our displacement wave. Here is our pressure wave. And they're phase shifted out from each other. And let me try to draw let me take a picture here. Let's see how well I can do it. Let's see how many does he have here. 1, 2. So we go. 1, 2, 3, fill in a fixed one. 4, 5, 6. Okay. So fixed. Fixed. Okay, so here's the atoms at some moment in time when the air is just sitting still and we haven't sent a sound wave through it.
Okay.
Now I come along and I'm going to send a sound wave through it. And so what that's going to cause to happen is I may compress these ones up together. So this one's going to move over this way, some like that. This one's going to move over some like that. This one's going to be compressed. Sorry. Let me draw this one still here. Let me draw these ones still here to help me keep my picture right as I fill in these other ones. So that one moves over, that one moves over, that one moves over, that one moves over. And then that one's like that one's there, that one's like that. Didn't draw these up very much the same height. That, and then it would have continued like that. Okay, the idea being that
notice that these are the atoms that didn't move, right?
Yes.
And sometimes the atom that didn't move, when I send a sound wave through it, is going to be at the point where it's where the atoms are most compressed, and another one's going to be at the point where they're least compressed. And one's going to be at the point where they're most compressed, and another fixed one's going to be at the point where they're least compressed. You with me so far?
Yeah.
Now the atoms here, the fixed atoms here, are where our position atoms are shifting 0. So this is modeling our fixed atoms, the ones that didn't shift. Because this was our Y. This one was our Y, this one right here was our P.
Oh, and so whether they're condensed or...
Yeah, so where this one didn't move, one of them was where it was the most compact, so here's where the pressure's highest. And then another place, the next place where it didn't move, which is right here, the pressure's at a low. And then the pressure's at a high, the pressure's at a high where it didn't move, and then the pressure's at a low where it didn't move. And so they're phase shifted off from each other. So an atom that's currently not moving with respect to time is either an atom that's in the middle of a high pressure place or an atom that's in the middle of a low pressure place.
How is an atom in a low pressure place not moving?
Intuitively, you can think about it as when it was, because it used to be in a high pressure place, right? You can think about it as these two atoms both collide into it and then bounce away, and then collide into it and then bounce away.
Oh, I see.
So
So-
it's like a node.
Yes.
Yes.
Now remember, this is lying, oversimplifying, to help you get the intuition.
Yeah.
Okay. That wasn't as bad as I thought it would be. That was honestly the thing I was most worried about explaining. Okay.
They're phased off from each other?
And then notice that the max pressure then that you can have in a wave, P max, is just equal to BKA. Sorry, that's a K. BKA,
Or in other words, where sign is 1.
Gotcha.
So that's one more equation that they throw out. Okay. So now let's move on to calculating the speed of one of these waves. Now I want to calculate the speed of one of these waves before we move on to examples, because we're going to use that bulk modulus thing again. So we're going to make reference to, made a similar picture, but a different one. But we're going to make use of this equation, so let me write it up here again. Let's see if I can remember it. B is equal to negative our change in pressure over our fractional change in volume. Okay, that's what we're going to need to use. Okay, so now we're going to talk about the speed that sound wave moves through some medium. Now we already calculated the speed of a transverse wave, right? Go back, think about the speed of a transverse wave. We said its velocity was equal to the square root of F, where F was like the tension in the string. The thing that's trying to get the string back to equilibrium, stop it from being out of shape, divided by mu, where mu was the density of the string,
Yes.
the mass per unit length,
Okay.
right? And notice that F tension is a restoring force in a string. In other words, if there were no F in a string, and I came and laid out a string in some shape, it would just stay in that shape. Right? If I laid out a string on this table in some shape, it stays in that shape until I apply tension to it. Then it straightens the string out.
Yes.
So this is a restoring force back to that equilibrium position of being straight, divided by the mass of the string, the thing that resists you putting it back into equilibrium. It's a lot harder to straighten out a really thick rope than it is to straighten out a really thin rope.
Yeah.
Okay, so we're going to have a similar thing now with velocity is equal to, I told you it's a common equation, velocity is equal to the square root of what's trying to restore the system back to equilibrium divided by what's resisting that. So when I'm talking to you, right here in the air, what is trying to make the air go back to its equilibrium position, stop those atoms from jiggling? That's exactly what the bulk modulus is. A high bulk modulus means there's a lot of resistance to that jiggling.
You mean the medium it's going through?
Right.
Okay.
It depends on the medium it's going through.
Yes.
And
That
this
makes
is
sense.
still velocity.
Yes, for the speed of sound. We'll derive this equation. This is just intuition. So give me intuition first, and then we'll figure it out. And then what do you think we divide by now?
Pressure.
Pressure or density.
Pressure's a good thought. Density.
Density? Like the density of the air?
Yes. And so, for example, the speed of sound goes faster through helium than it does just through air. Speed of sound goes faster through helium than it does through air, which is one of the reasons your voice sounds funny in helium. The sound's actually traveling faster in helium.
Oh, okay.
And that's because helium is a lot less dense than air. A helium atom is tiny compared to like oxygen molecules and nitrogen molecules.
Yeah, that makes sense.
Okay, so we expect something like this. Well, we expect this exact equation. This is exactly what we're going to derive. Now let's derive it.
Okay, so we're back to, this is a cylinder pipe, and I've got some piston in the pipe. So that completely seals off the pipe, some circular, like rubber cap that I'm going to slide into the pipe,
Okay.
to create displacement. Some piston, but completely frictionless piston.
Wouldn't air and water escape out of it then?
No, it perfectly seals it completely off,
But
and it's also perfectly frictionless. It doesn't exist.
Okay.
Okay, so we've got this piston here. Let me shift a little bit this way. I'm hugging this side of the board and I don't know why. So we have our our cylinder pipe, our cylinder tube, or whatever, and we have some piston right here, okay? And we have air molecules inside over here, and we have air molecules outside over here, and right now the pressure is the exact same.
Okay.
So on this side of the piston, we have a force pushing that way of pressure times the area for the force pushing the piston this way. Maybe shift this over some. P times A for the force pushing that way on the piston, and then inside there we have the same pressure pushing on the same area that way. And so it's not moving. Everything's in equilibrium.
Okay.
Now to produce a sound wave, I'm going to change the pressure over here to create a force to start pushing on that. Right? That's essentially what I do when I talk. I create a higher pressure somehow in my throat, which then starts pushing on the air.
Okay.
Then why do you need vocal cords for that?
You need something to vibrate. But it's ultimately creating a pressure difference. That's what it's doing. Okay, forget your vocal cords. Speaker. What does that speaker start doing? It starts pushing. It starts creating pressure differences.
Yeah.
Okay. So that's what we're going to do.
So we're going to go forward sometime, and when we go forward sometime, the picture is now going to look like this. And that imaginary piston that has no mass that we're pushing forward is going to move some distance forward like this. So now we're over here pushing on it with some, we had some change of pressure, so P plus delta P times A. Right?
Yes.
Which starts pushing it forward. The sound wave that it produced, we'll say, has traveled this far in that time. We're pushing forward on this piston. This piston is moving forward at some constant velocity. Now we're going to say V sub y. Don't get confused. This is just to follow
Same as your position.
same variables that we used when we derived the speed of a transverse wave. It's very similar. We're doing almost identical things.
Okay.
So this piston now is moving forward with velocity P sub y. The speed of sound that produces has already moved this far, however far that's gone.
Okay.
Because if I start pushing to create a sound right here, I don't have to push the air all the way to you for you to hear it. Because when I just push this air, it starts a jiggling effect. And that jiggling effect travels much faster than I actually push the air.
Yeah.
And so the jiggling effect has gone this far. You with me so far? So I'm going to call V sub y how fast the air here is moving. Now all this air is being pushed forward, so this air right here is also moving forward at V sub y.
So all the air that has higher pressure now is going forward this way with V sub y. But over here, none of the air over here is moving yet, and this is the speed of sound that gets things jiggling.
Would there be pressure pushing this way then?
There's still pressure pushing this way over here,
Okay.
which is still P times A, same as it was before. That is air that it has not been communicated to that, hey, this thing has started moving. The air over here doesn't know yet.
Okay.
Okay. So, we're going to do something similar to what we did last time. We're going to have to talk about the momentum. Since I already have pressure up here, I can't use P for momentum. I'm going to use L for momentum. So don't get confused by the fact that I'm going to use L for momentum because we already use P. Alright?
Physics.
So, going to use L for momentum for a second here. And let's remind ourselves of something that we reminded ourselves of last time, but not bad to do it again. The derivative of momentum with respect to time is equal to mass times the derivative of velocity with respect to time.
What's the derivative of velocity with respect to that?
It's acceleration.
Acceleration,
But that's just a force.
which is just a force. Perfect. So that's just a force.
Momentum
So
is
if we
just a force.
integrate a force over time, no, the change in momentum with respect to time is force.
Oh, duh.
So if we integrate a force over some time interval,
You'll
from
get
T1 to T2, we're going to be left with a change in momentum.
okay.
Force times time gives you a change in momentum. And since we use that so much, we call the force times time your impulse.
Yes.
Okay.
Force
So-
times time or derivative time?
Since the derivative of momentum with respect to time gives you force, then the integral of force with respect to time gives you momentum.
Then what's the impulse?
We just call impulse, when you have specifically a force times a time, we call it an impulse.
So force times the time is impulse.
Yes. We call that an impulse, it gives you a change in momentum. So the units are the same as momentum.
Okay.
With me?
Yeah.
Okay, so we're going to have to use this fact over here. So I'm going to calculate the momentum of this thing. I'm going to multiply it by time, and that has to be equal to the net force acting on this thing. So first, let's calculate the mass that we're even talking about.
Oh,
The
so
mass of
we-
air that we're talking about, yeah.
Okay.
Because notice that before we started compressing it, all the air we were talking about was right here. It was this air, sorry, that dot line was meant to line up with this dot line. Can't believe I missed so bad. So we had all this air, and then we start pushing, and so now we have all this air right here. Because remember, this is like the front of the air that barely knows that, hey, something's going on. If you go barely past that point, we don't know anything's going on yet.
Okay.
So this is all the air that we're talking about so far. You with me?
Mm-hmm.
And so what is the mass of all that air? That's the mass that we're going to be talking about.
Well, how do you find that?
Well, what's this distance right here?
What is that distance?
That distance is the speed of sound times time. This distance is the speed of sound times time. And that's how far sound has traveled so far from when we started the process.
Speed times time is.
And that's the V that we're looking for. It's the speed of sound.
How is speed times time a distance?
If I'm going 10 miles an hour for an hour,
Okay.
speed times time gives you distance. Okay.
Okay.
So this is the V that we're looking for,
Okay.
the speed of sound.
Yes.
But the speed of sound times time is what this distance is, right?
Okay.
And so the mass that we're talking about is going to be equal to the volume here. The volume there is going to be VT times A. Gives me the volume.
Mm-hmm.
Times our density, which is rho.
Volume?
Volume times mass per unit volume gives you mass.
Rho.
Oh, that's a rho. Yeah, sorry. Not a P. Rho. I don't know how I can make that look more like a rho. I don't know. Should we like curve it at the bottom? Maybe something like that. Does that help?
Yeah, that helps.
Okay. So I'll try and curve it on the bottom. Now I'm making it massive.
It's not. Okay.
Something. Rho. Density. The same thing that shows up right here. Rho. The density of air.
Okay.
The density of air in equilibrium. Rho. Okay, so there is our mass, right? So our change in momentum of the system, we have all this mass, and now we have it moving forward with speed v sub y.
Yes.
So our total momentum of our system is mass times v sub y. That's our total momentum. Our total change in momentum, because our momentum initially was 0.
Gotcha.
So our total momentum and our change in momentum are the same thing, and this is going to be equal to our force times our time. Right?
Force times your time.
Force times time gives me my change in momentum.
I'm sorry, how did you get the part on the left again? Mass times Vy.
That's just the momentum of all this air.
How do you know that's the momentum?
So we calculate the mass of all the air, right?
Okay.
And down here, we have all that air. Now it's just compressed more, but it's still the same amount of air, so it's the same amount of mass.
Yes.
And it's all now moving forward with velocity v sub y.
Okay, I see where we're at.
Okay, so that's the total momentum of our system. And then it has to be equal to the net force on our system times our time.
Yes.
Okay, what is the net force on our system? If we call that positive force, that negative force, we have this force pushing that way and this force pushing that way.
Okay.
So our net force is going to be our change in pressure times A. There's our net force times time.
Yeah.
Yep. Good with that?
Mm-hmm.
All right, let's make our substitution for mass on this side. So we get Vt times A times rho is equal to our change in pressure times A times T. That's an A, not a delta. Good?
So you can get rid of your T's and your A's?
We can get rid of our T's and our A's, sure. So V times rho, and remember that's a velocity V, that's our speed of sound, that's what we're looking for.
Yep.
Is equal to delta P. Did I do everything right? Looks like it.
Yeah.
Okay. From up here, I know that negative delta P is equal to B times delta V over V.
Where negative V times that is your delta P.
Right. So, but let's just play with this for just a second here. We have B times, let's plug in our delta V and our V. So we went from here to this, right?
Yes.
So our delta V is this right here. This is our change in volume.
Change in
We lost this volume right here.
Yes.
So our delta V is a negative number. Negative. And what is the volume of this piece right here? That's going to be V sub y times T times A.
V sub y times T times A.
V sub y times T is this distance. Because V sub y is how fast I'm moving that piston forward.
In time. Okay.
So V sub y times T gives me this distance, times A gives me the volume.
Gotcha.
And our initial volume was V sub T times A. Or V times T times A. Where V is just the speed of sound now. And not how fast we're moving the air for it.
Okay.
Good?
I think so.
Which is equal to now negative Vy over V times B.
Yes.
So we get delta P is equal to Vy over V times B. Right?
Mm-hmm.
Okay.
So we're going to make that substitution down here now.
Aren't you looking? Oh, I see. I see
Yes.
over here.
So we got V sub y over V times B. Oops. I lost my v sub y over here.
I was gonna
We
say,
just
how are
replaced
you
the
gonna
m.
get rid of your v sub y?
Yeah, so we needed a v sub y here, velocity times mass, so we still need v sub y here.
Okay.
Okay, so now v sub y cancels out with v sub y. I'll move the v to the other side, so we're going to get v squared times rho is equal to b,
Or v is equal to b over rho.
where v is equal to the square root of b over rho.
Okay. So it's basically just what we did before.
Almost the exact same thing. Yep.
Okay.
And we won't derive this one, but we'll give you the last one. V is equal to the square root of y over lambda again. Or not lambda. Mu? I think it's gonna be mu. Maybe we'll double check.
Then what's the difference?
Did we already do this?
Maybe.
No, it's gonna be over rho. Okay, that actually makes sense. Over rho. Okay, so here's our last one. And this equation right here has to do with not when you're sending sound through a medium, but when you're sending it through just a rod. So if I had now just a metal rod, like a piece of rebar.
But isn't that still through a medium?
Yeah, it's still through a medium, but now when we talk about compressing or expanding steel, we're not talking about, we basically made so that the compressions and expansions only happen in one direction. And so that's Young's modulus that you looked up from that previous section.
Young's modulus?
Yes, Young's modulus.
Did we go over that?
Uh-huh. Young's modulus, bulk modulus. So bulk modulus has to do with when you're like expanding in 3 dimensions. Young's modulus is basically when all the expansion can only happen in 1 dimension.
Oh, I think I remember now.
So when I send a pressure wave through sound, it kind of goes out everywhere in all 3 dimensions.
Yes.
When I send a pressure wave to you down a steel rod, it kind of just goes straight down the rod in 1 dimension.
Is that kind of like talking through a pipe is like?
No. No. No.
Okay.
So what talking through a piece of rebar is like.
Talking through a piece of rebar.
Yeah, a long steel.
Can you really talk through like rebar and like steel and whatnot?
You can send vibrations through them.
So if you have like a massive steel wall and you have 2 people on each side and they can't hear like underneath the wall or anything, then they can talk to each other through that.
Just send
Probably
it.
not well.
But you can hear something.
You can send vibrations. That's what you can do.
So you don't necessarily hear it, but there's vibrations coming.
Yeah, I don't know if you're going to hear us. I don't know if you're going to hear a frequency that you're used to hearing.
Okay. That makes
And
sense.
there probably have a lot to be with how that's actually set up, because I mean, the structure could absorb a lot of it. Because I mean, when you talk about steel wall, a steel wall doesn't naturally have a lot of wiggle room, and so there's going to be a ton just lost to friction really quick. So you're going to lose a lot of energy.
The friction.
Yeah, because it's like being held in place, and there's things you have to fight. Whereas when I'm talking through air, there's nothing really stopping this air from shaking.
So sound does move faster through other materials, but it's not as effective.
Right. You can't hear it as well. I mean, okay, obvious example. People talking when you're underwater.
Yeah.
The sound gets to you faster, but now it's not near as intense, and you can't hear it very well.
Okay. That makes sense.
What's the Y?
That's a constant that depends on your material. It's your material's resistance to compress.
So it's just like a mu or a V?
Yep. Like, not like a mu. Mu was density per unit length. That doesn't tell you about anything about its resistance to compress or stretch. So imagine that I took a steel rod, and then imagine I had Play-Doh, which was just as dense as steel. I can compress and stretch Play-Doh. That has a very low Young's modulus.
Yes.
I can't compress and stretch steel. It has a very high Young's modulus. So it depends on the actual material, what your Y is. It's not just a measure of mass per unit length. That's what this is. Okay? And so those are the three equations that you'll need for calculating sound, speeds of sound. They give you speed of sound in a gas. I don't know how much I want to get into this yet because it's bringing up a lot of stuff that we'll be doing in the next 4 chapters.
Okay. Wouldn't sound just move the same through a gas?
So here's how sound moves through a gas. We already have it. V is equal to the square root of V over rho. Here's our problem. The bulk modulus for a gas changes a lot with temperature.
Yes?
Yes.
The medium you're moving through changes with temperature?
No, for specifically when we're talking about a gas.
So let's say just nitrogen.
No, I'm talking about even the gas right here in this room is related to temperature. And the higher the temperature, the higher the bulk modulus. And so actually sound travels faster through hot air than it does through cold air.
Does that make it easier to hear?
It makes the sound travel faster. Oh, it does. Well, I don't know what other effects it has, but it for sure makes the sound travel faster. And it can make significant differences relatively fast.
Okay.
And so if you were to go look up the bulk modulus for air, then they give you the bulk modulus for air at like 20 degrees Celsius. Because it's different at 3 degrees Celsius and 40 degrees Celsius and 50 degrees Celsius. That's something special with gases. The bulk modulus for water doesn't really change. Water, whether you heat it up or cool it down, water is water. Gas changes a lot with temperature. If I take a balloon and I heat it up, the balloon expands. I go stick it in the freezer, the balloon contracts. I take a balloon, fill it up with water, heat it up, stays the same size. Cool it down, stays the same size. Roughly.
Yeah.
So a lot of materials don't really change with temperature. I can take this table outside on a hot day, and then I can take this table outside in the middle of winter. It stays roughly the same size. Its bulk modulus doesn't really change. With temperature, or with gases, that's very much not the case. Gases change a lot with temperature. And so this is, we can calculate the speed of sound, we can calculate the speed of sound here as an approximation, and we typically use the bulk modulus for air at 20 degrees Celsius, and we get 344 meters per second. But that's a very rough approximation, and it changes a lot depending on the temperature. And so the actual equation, when we're talking about a gas, is V is equal to the square root of, we're going to have some constant up here, gamma, times, I think R is in the numerator, we'll come back to that R, times temperature, divided by M, capital M, where M is, what do we call it? The molar mass. And we'll get into these concepts here in a second. Yeah, I don't really want to give it to you too much right now because we haven't even gone over what a mole is.
Well, I already know what a mole is.
It's one of those things that dig in the ground. You can't see.
You know what a mole is?
Well, we went over it
Did you
in
take chemistry?
Me?
Yeah.
No.
No? Just beer?
Well, I mean, eighth grade.
If you've taken chemistry, we could easily go over this. If you haven't, then the next 4 sections are going to make this make sense. But you've already taken chemistry. Okay, so this is the same R that you dealt with in chemistry.
I don't remember the R though.
It's a new constant that makes working with what's the other constant called? Gravitos constant or something like that. How many atoms are in a mole?
Oh,
Okay, that number.
okay.
You remember working with that constant a lot?
the mole constant of how
Yeah.
many atoms?
So rather than having the mass, rather than having m here, the mass of individual atoms that we're talking about times the number of atoms helps so that we don't have to keep track of the count of the actual atoms here. So you had equations where you actually use the number of atoms, use one constant there. You had another equation where you just use the mass of the atoms and you use this r here. So you actually use that r a lot even if you don't remember. So this r, this is just a constant we're going to calculate. It's kind of like the g in Newton's equation. Newton's equations for gravity, you just had g in there. That's kind of like what that r is.
Okay, I see.
It's just going to be thrown in there. The t here, that's the temperature. Temperature goes up, or speed goes up. M, this is like the mass of the gas. A gas composed of oxygen atoms has a lot more mass than that same gas composed of helium atoms. Helium atoms are a lot smaller. The gamma here, this is like how much does gas respond to heat?
And it depends on the gas, right?
Yeah, it depends on the gas. Some gases respond a lot to heat, some gases not so much. So constant, this is just a constant like the g in Newton's equation. This is a property of the gas. This is the mass of the gas, and this is whatever the temperature is. And so here's the speed equation for specifically when we're talking about a gas. And this is the same thing as this, just with temperature brought in.
Gotcha.
And the book walks you through some explanation about how it went from this to this. I don't want to spend too much time on it, but it's not that much. Okay. So with the speeds of sound in air now, we kind of like got through the rough math now. So maybe we could do some examples real quick. So let's go back now and look for examples. First example from, in a sinusoidal sound wave of moderate loudness, the maximum pressure variations are 3 times 10 to the minus 2 pascals. So we've got some sinusoidal wave of sound, and we know that the max pressure fluctuation that we're getting, P max, is equal to 3.0, yeah, 3.0 times 10 to the minus 2 pascals.
Okay.
So, in a sinusoidal sound wave of moderate loudness, the maximum pressure variations are 3.0 times 10 to the minus 2 pascals above and below atmospheric pressure.
Okay.
Atmospheric pressure, remember when we model a pressure wave, so I say the pressure of the wave is changing like this. What's the 0 here? That's atmospheric pressure.
Is that so one? Okay,
1 atmosphere.
gotcha.
That's when it's at equilibrium.
Okay.
So that's why it's worded that way. Okay. Find the corresponding maximum displacement if the frequency is 1000 hertz. So we're trying to find the maximum displacement that the atoms jiggle if frequency is 100 hertz. So we know frequency is, I think I'm saying 100, but I think I read 1000.
Yeah, you read 1000.
1000 hertz. Okay. So frequency is 1000 hertz. We're looking for the maximum displacement.
Is that your amplitude?
Yeah, that's exactly right. That's the A.
Okay.
So we're looking for the A here. What's our A? Some other things we know. We know the speed of sound is 344 meters per second. I don't know if that's going to come up. P max, remember, P max is BKA. So I
Yes.
know that B times K times A is equal to 3.0 times 10 to the minus 2, right?
Yes.
So I know that A, that's what I'm looking for, is equal to 3.0 times 10 to the minus 2 over B times K. Now, I assume they have to give us the bulk modulus. The bulk modulus is 1.42 times 10 to the 5. So they give us B. B is 1.42 times 10 to the 5.
Someone asked me to get this to you.
Oh, thank you.
Sure thing.
Yes.
Guys' test.
Sorry, guys.
You're fine.
If we had known, we would have learned them.
All right.
It's like-
So that's it. That's all we know. Okay, B. So we know what B is. We're already given that, so our only problem now is to find K. And once we know K, we can figure out our amplitude A, right?
Yes.
So what is K?
K.
K is our wave number, right?
Yes.
So I know that K is equal to 2 pi over lambda, right?
Mm-hmm.
Now I know that velocity is equal to frequency times lambda.
And you know velocity and you know frequency.
And I know velocity and I know frequency.
Okay.
So K then is equal to frequency over 2 pi times the frequency over the speed, right?
Yes.
Just substituting in right there. Okay. So we know our K, we know our B, we can calculate our A. Let's plug it all in. So our K is going to be 2 pi times the frequency. Frequency was 1,000. So our K is 2,000 pi divided by our speed, which is 344. That gets me my K, which is roughly 18.3. So now I'm going to take 3.0 times 10 to the minus 2 divided by B, which is 1.42 times 10 to the 5 times K, which we already calculated. And I get roughly 1.16 times 10 to the minus 8.
Those are really small.
And that's how much the air atoms are jiggling. If I were speaking with a perfect frequency of 1,000 hertz, then that means that the air molecules would have been jiggling back and forth 1.16 times 10 to the minus 8 meters. They're not jiggling very much.
Well, considering it's an
Gotcha.
atom.
Okay.
Huh?
Considering it's an atom.
Yeah. A lot relative to the size of the atoms, but not much. Okay, next example. A sound wave that enters a human ear sets the eardrum into oscillations, which in turn causes oscillations of the ocelles, a chain of 3 tiny bones in the middle of the ear. The ocelles transmit this oscillation to the fluid, mostly water, in the inner ear. There, the fluid motion disturbs hair cells that send nerve impulses to the brain with information about the sound. The area of the moving part of the eardrum is 43 meters squared, or millimeters squared, square millimeters.
Meters squared.
Yeah, not meters, millimeters.
Did you break eardrum?
So we're going to have, completely lying picture, but roughly, what we have is, we've got some bone here. The area right there is 43 millimeters square. And then the bone's gonna get smaller to some smaller area. The air, this is a part open to the air, so the air outside pushes on this part of the bone,
Okay.
which then pushes on a fluid on this side. So this part pushes on fluid, air pushes on this part. Roughly what's happening. Nothing like what it looks like, but physically get an intuition for what's happening. And this has area over here of 3.2 millimeters squared, so it gets much smaller.
Oh yeah.
Okay. For the sound in example 16.1, determine A, the pressure amplitude and B, the displacement amplitude in the fluid of the inner ear, in which the speed of sound is 1,500 meters per second. So inside of here, so this is now fluid, this right here is air. The speed of sound here, excuse me, which I'll call, I don't know, V of the fluid, is equal to 1,500 meters per second. And we're looking for, I forgot what we were looking for, A, the pressure amplitude. So A, we're looking for P max inside the ear, over here, not P max out here.
Okay.
And B, we're looking for the displacement amplitude, just A. And B, we're looking for A, the displacement amplitude of the fluid inside the ear.
Wouldn't you have to find A to get P max?
And let's make sure that we understand that this is of a fluid and of the fluid. It's not the same thing that we had outside. So we're repeating the same problem here, so we still have all this for outside, and then here's what's happening inside the ear, right?
Yes. Does it give us our B?
Our B?
Yeah.
Our B inside the fluid is 1,500.
No, our B.
Bulk.
Our B, our bulk.
Oh, our bulk modulus. Our bulk modulus for water, yeah, we're probably gonna need that. Maybe we won't. I don't know. Let me think for a second.
Is it just water?
So I know that P max out here, I know P max out here, so I can figure out P max in here, because it's just areas changing. But it has to be the same force. Whatever force I apply on this side of this bone has to be communicated over here.
So how would you represent that?
So the force over here, force is pressure times area. So the max force out there is P max times this area,
I see.
which I'll call A1. We'll call this one A1 and this one A2. P max times A1 has to be equal to P max of the fluid times A2. Or in other words, P max of the fluid is equal to A1 over A2 times P max of the air that we had outside, which we already knew.
In pascals, yeah.
Yep. So this will give us roughly our maximum pressure. Which is going to be 43 divided by 3.2. Since I just care about the ratio of these two, I don't need to convert them to meters.
Yep.
So all that cancels out. Times P max, which is 3.0 times 10 to the minus 2. And that's 0.40. So this comes out to 0.40 pascals. So it's gone up more than tenfold, the pressure in there.
Okay.
And now we were also looking for the amplitude inside. Let's see, I know, maybe I will need the bulk modulus. Because I know that A sub F is equal to our bulk modulus of the fluid divided by,
Your K.
I'm writing the same thing again.
Yeah.
Oops. The max pressure, P max of our fluid, divided by the bulk modulus of our fluid times our K.
So it looks like we're just finding for K and
So, let's see. We must have looked at the bulk modulus somewhere. Let's see if they did this without the bulk modulus. Although don't care. That's for part A. Where did I start? To find the maximum displacement. Okay, yeah, they did look it up. 2.18 times 10 to the 9 for our bulk modulus of our fluid. Bulk modulus of our fluid is equal
Pretty
to,
bulky.
what did I just say, 2.18?
2.19.
2.18 times 10 to the 9. Okay, and now we still need to find our K, and this is a K when we get inside the fluid, because obviously the weight is different here.
Well, do you
We
know
can
your
calculate that
frequency?
the same way as this one. So the K inside of our fluid is equal to 2 pi times our frequency divided by the velocity in the fluid. Now the frequency is the same on both ends. How do I know that the frequency is the same?
Yeah.
The frequency is how it's pushing back and forth on this bone.
Okay.
And how this part of the bone moves back and forth is identical to how this part of the bone moves back and forth.
Because it's all the same bone.
Yeah. It's not like the bone's compressing and spreading out like that. It's moving like this, in unison. The bone's vibrating together. So the frequency is going to be the same for both of them.
Is frequency the same for that then?
The same frequency we had here, yeah. 1,000 hertz in both cases. But the velocity, the speed of sound inside the fluid is different. So we'll get a different K than we had over here, but we still use the same frequency.
Okay.
So our K then, we get 2,000 times pi divided by, the velocity of our fluid is 1,500, and it comes out to 4.2. Doesn't matter what it comes out to, because that's not what we were looking for. I just need to use that number now to calculate this. This is what we cared about.
Amplitude.
So let's calculate that now. So our amplitude, we go back to P max. So I take my max pressure divided by our bulk modulus, 2.18 times 10 to the 9. Times the K that we just calculated, which was at 4.18. And it comes down to 4.4 times 10 to the minus 11. Which is obviously much less than in air. So the air was moving back and forth this much. The water atoms are jiggling much less for communicating the same wave.
And they're communicating it a lot faster.
And they're communicating it a lot faster.
Gotcha.
4.4 times 10 to the minus 11. Yes. Okay. Speed of sound. Let's do one of these. Probably doesn't matter which one. Sonar is interesting. We'll do the one with sonar. A ship uses a sonar system to locate underwater objects, finding the speed of sound waves in water. Okay, that wasn't quite as cool as I thought.
Okay.
So we're just finding the speed of sound wave in water and find the wavelength of a 262 hertz wave. So our frequency is 262 hertz. Frequency is 262 hertz. We're trying to find the speed of a sound wave in water,
Okay.
which means we need the bulk modulus for water. I erased that, but I can still see it here. B is equal to 2.18 times 10 to the 9. Oops. 2.18 times 10 to the 9. Okay. So we have our frequency, our bulk modulus for water.
Why does boat pick his speed?
Excuse me. Well, our speed that we calculated before, just barely, for a sound wave, is our bulk modulus divided by rho, right?
Oh yeah.
So you just need the density of water?
Which we already know the density of water.
We do?
Yeah.
It's like 1,000.
One-
I mean,
No, just 1,000
just 1,000.
Mhm.
So
1,000 what?
kilograms per cubic meter. Or 1 gram per cubic centimeter.
Oh.
So, this is actually real easy. So it's just the square root of 2.18 times 10 to the 9 divided by 1,000, which is 1,476. So I should write 1,480 meters per second. Oh, and we need to calculate the wavelength, right?
Wavelength is k, right?
It's
I mean lambda.
Yeah. And so we know that velocity is equal to lambda times frequency. And so lambda is equal to velocity divided by frequency.
Pretty straightforward.
Pretty straightforward. So we take our velocity, we divide it by our frequency, and that gives us 5.64 meters. Okay, so now let's check. V, 1,480 meters per second, yep. Wavelength, 5.65. And that's because the author wasn't smart and he used his already rounded number in calculating that rather than using his unrounded number. So he's compounding his rounding errors.
Wouldn't you want to use your original number?
Right, I use the original number, so I got 5.64. The author got something
Oh,
barely
yeah.
higher than me,
I see.
which means he used a rounded number. So, bad on him. Okay. Sound intensity now.
Sound intensity.
Sound intensity. We already talked about intensity a bit.
Yeah.
So, intensity, you might remember we talked about intensity as power per unit area. Power over area. So when we were talking about the intensity of the sound wave, you might remember we had something like, I can't remember exactly how we wrote it, but it was something like it's the power at that point divided by 4 pi r squared.
Yeah.
We use an equation something like that. It's taking the power divided by 4 pi r squared because that was the area of a sphere. And so if a sound wave is traveling out in a perfect sphere, that gives you its intensity at any point.
In a perfect sphere though, but it's
In a
not.
perfect sphere. It's a good approximation for a law of sound.
Okay.
So we're going to be doing something similar to that. So we need to come back to our power equations. And we need to remember 2 ways that we talked about getting power. Power is the amount of work you do per unit time. So work over time gives you power.
Okay.
But work you can also think about as force times x over time.
Force times x.
Times your displacement. Force times distance gives you work.
Isn't that just momentum?
Which we can write this as then F times x over t is v. And so we often calculate a power using a force times a velocity.
That's right.
Common way that we do it. So those are the 2 common ways that we talk about it. So we're going to be talking about power in a sound wave. And the way that we're going to be talking about power in a sound wave is this exact thing. Well, we're going to be talking about intensity of a sound wave. So remember then intensity was equal to power over area.
Yeah.
Or in other words, we're going to represent it as force over area times velocity. You with me so far?
Yep.
Because there's one more way that we're going to talk about it. What is force over area? Newtons per meter squared. Newtons per square meter.
Newtons per square meter.
Pascals. So this is the same thing as pressure times velocity.
Pressure.
Pressure is force over area. If I apply the same force over a small area, that produces high pressure.
That's right. Okay.
Same force over a lot of area produces low pressure. So that's how we're going to talk about intensity. So intensity, we're going to model as our our power or our pressure function times our velocity function. Now, how do we get the velocity function?
Isn't it just the derivative of your position function?
Derivative of your position function, partial derivative of your position function with respect to time. Changing a position with respect to time is your velocity.
With respect to time? Okay. Yes.
Okay? And dy dt, we know what that is from looking up there. Well, I'm not sure how he's actually out to write this. Let's just substitute everything in. Who cares where the author's going? We're coming up with our intensity equation. So our intensity equation is going to be pressure times velocity. Let's start substituting in. We know our pressure function, that's right here, and we can get our velocity function, that's right here. So let's just write it all out. So our pressure function is B times K times A times the sine of Kx minus omega t, right?
Mm-hmm.
And then we have multiplied by our velocity function. So we got to take the partial derivative of this with respect to time.
So it's negative omega times...
Comes back out positive because the omega is negative, and then when you take the derivative of cosine,
That's
you get
right.
negative sine. Right? Omega A sine Kx minus omega t.
Yeah.
Put that all together, and what do you got? We've
We
got,
have two A's and two sines.
right, so we got bk omega A squared times sine squared of Kx minus omega t. For our instantaneous intensity.
Just bk omega times A squared.
Times sine squared. Sine squared doesn't go away.
Oh, I'm thinking of your... Is there such thing as like an intensity max?
Yeah, your maximum intensity, that's a thing. Now, intensity we use a little bit different from other variables.
Okay.
When I was using I here, this is our what we would call our instantaneous intensity. By definition, intensity is your average instantaneous intensity. So it's one of those words that anytime you hear intensity, it actually means an average. Your average instantaneous intensity is what we mean by intensity. So our intensity, that when the book actually writes an I, they don't mean this. So this is our instantaneous intensity. When the book, anytime the book uses an I, anytime they talk about intensity, they mean the average of this thing. What does this thing average out to?
Well, how do you find the average of that?
B, K, omega, and A squared are all constants. The only thing changing is what the sine function spits out. And the average of sine squared, told you this last time, is 1/2. Sine squared function averages out to 1/2.
Yes.
So intensity is 1/2 bk omega A squared. Because by definition, an intensity is an average. Non-instantaneous value.
Okay.
Okay. So the book's going to give you write out 3 equations that they use for intensity. We'll write them all out. We have our first one here. The other ones are just from substitutions. So we have I is equal to 1/2 bk omega times A squared. They're also going to write it as our max pressure squared all over 2 times rho times V. And then they're also going to write it out as max pressure squared divided by 2 times the square root of rho times V. And these other two equations just come from substitutions, using the fact that Pmax is equal to BKA and using the fact that velocity is equal to the square root of B over rho. So using those two substitutions, all these are saying the same thing.
Okay, gotcha.
And not seeing the value in the right, plugging them in and saying that. You can reverse those pretty easily. Okay. Now, we have intensity, and then we have what we call sound intensity.
Sound intensity? Is
Yes,
it different?
intensity and sound intensity. Yes, they are different. Now, what intensity is meant to model is actually how much energy is in that sound wave. Like how many joules is that wave carrying along?
Okay.
Sound intensity is meant to capture intuition for how loud a sound sounds to you. And we already talked about this a little bit. Just because I double the amount of energy in a wave that I send out doesn't mean it sounds twice as loud to you, necessarily. And the example I used for you was, it's not a one-to-one thing, but it's good intuition, like a light in a room. If I turn on a light in a room, it brightens up the room. If I turn on a second light that's just as light as your first light, it doesn't make the room seem twice as bright to you. Even though the intensity of light in that room is twice as much, it doesn't seem twice as bright to you.
Okay.
So the intensity in the room doubled. What we might call the sight intensity didn't double. So I'm talking to you now with the sound with some intensity. If I double the intensity, it doesn't sound twice as loud. So the sound intensity doesn't necessarily double. So intensity is how much energy is actually in the wave. Sound intensity is meant to capture how loud it sounds to you.
Gotcha.
Okay. So here's our sound intensity equation. And it's going to be a log equation, which,
Logarithmic?
yes.
Okay.
Why logs? Think about how a log equation grows. A log equation grows like this. Right?
Mm-hmm.
Which means in the beginning, a little bit more makes a big difference. But after so much doesn't make much of a difference.
Yeah.
Right? If we're already right here, and I add a ton to right there, that doesn't make near as much difference as going from right here to right here. Right? This might be turning on a really bright light in a dark room. This might be turning on a really bright light in a bright room. Makes almost no difference, whereas in the other case it makes a huge difference.
Okay.
Sound works the same way. So, and sound intensity, you've already heard about the units of sound intensity. You could probably guess it. When your teachers tell you to quiet down, they say, let's drop the sound in here by
3 degrees.
3 degrees. They don't say degrees.
They say by like 5?
5. What's the units they say?
They always just said just one thing.
Big round couple levels.
They didn't say decibels.
That's
Decibels? Or decibel? Can we drop the sound intensity here by 10 decibels? You've never heard of a decibel?
I've heard of decibels.
Okay.
Decibel.
Yeah. I intentionally pronounced it a little bit weird so that you can see where it comes from.
Okay.
Like decimal.
So the unit is a bell,
Oh.
and we typically talk about tenths of bells, which is a decibel, and then everyone pronounces it decibels. Kind of like how do you pronounce a thermometer?
Thermometer.
Right. But it's a meter that measures thermal activity. It's a thermometer. Everyone says thermometer. Fine. I don't know.
What is a bell?
So a bell is just a unit of sound intensity. Why bell? It's just the last name of the. It's named after what's his name?
Graham Bell.
Huh?
Oh no, Graham Bell.
Was that his first name? Graham? Inventor of the telephone.
Yeah, Graham Bell.
Yeah.
His first name's Graham. For some reason, I thought it started with an A.
That might be his middle name. But it's one of his names.
Anyways, his last name is where it comes from. The inventor of telephone.
Alexander Graham Bell.
There we go.
Nice.
See, I'd say Alexander Bell. Yeah, I was pretty sure it started with an A.
I
Okay.
don't know why, but I always called him Graham Bell.
Anyways, so our decibel system, let's quickly draw it up and get some examples here. Well, maybe we'll write out the equation really first. So sound intensity, which I may write a beta, that's how your equation has it written. Sound intensity beta is equal to 10 decibels. We'll put the units in there, even though I usually hate putting those on equations, just because it's not 10 bells, it's 10 decibels. Times the log base 10 of intensity over some base level intensity.
Okay, what is that saying?
Now I'm going to write this a little bit different, simpler. 10 times log base 10 to the I over I naught, if you just remember that your units are decibels.
dB decibel.
That meant a decibel, put the units on there.
That's unit.
Yeah. You'll see it like that in your book. Here's how I'm going to write it from here on out.
Okay, so why do you...
So let's cover the variables. 10 is obviously just 10. Now log, anytime you see log without a base on it, it's assumed to be base 10.
Yes, why do you have your 10 at the first? Why 10?
You'll see here in a second.
Okay.
I naught is the minimum intensity people can hear.
So it's constant.
Yeah, it's some base level intensity.
But isn't it different for everyone else?
Yeah, it's a rough average for all people. So
Okay.
10 to the negative 12, I naught is 10 to the minus 12 watts per meter squared. So base level sound. And then I, right here, is the intensity of the wave that you're trying to calculate the sound intensity for.
Okay.
So that's a variable. You plug in I, and it spits out your beta, which is your sound intensity. All right, so really quickly, notice what happens when we plug I naught into this equation. So what is B naught? Or what's beta naught equal to?
I naught over I naught, which is just
It's just
10 to the log.
I naught over I naught is log of 1. What's the log of 1?
I don't know logs.
We didn't do logs.
We did do logs.
You just don't remember?
I missed out on half of my algebra.
Okay. If you know that log base A of B equals C, that is identical to, this says the exact same thing as A to the C equals B. It gives you the exponent. A log takes a number, spits out the exponent. An exponential takes an exponent, spits out a number.
So C in this case would be 0.
So in our case, yes, C is 0.
Okay.
So log of 1 is 0. Because 10 to 0 equals 1. So this is 0, so it's equal to 0.
So your sound intense, well yeah, that makes sense.
So
Okay.
our sound intensity is 0 when our intensity is the minimum sound a human being could possibly hear.
The intensity isn't 0. The sound
Not the intensity. The intensity was this.
Gotcha.
So we played some sound.
Okay.
And the sound that we played gave us an intensity level of 0.
Yes, that makes sense.
Notice what happens if we tried to plug in a number smaller than I naught up here.
You mean like 1/2?
Yeah, so the whole thing comes out something like 1/2.
Okay, what happens?
Oh, maybe that's not. Sorry. I was thinking down a bad path.
Okay.
Do what?
Never mind. Forget what I just said. forget it. Anyways, so we have it set up now so that sound intensity is 0 when you play the minimum sound a human being can possibly hear.
Okay.
You with me? And then we have it set up so that when you play an intensity of I equal to, let's see what they have here, 1 watt per meter squared. Now let's calculate what the sound intensity is of that. And I'll call that beta 1. So beta 1 is equal to 10 times the log. Actually, let's not do that yet. Let's just increase our sound intensity by a factor of 10 now. Let's do that first.
So log base 10 of 10.
Yeah, so really quick, let's say now, what if I replace I naught with 10 I naught? So what if I play something 10 times, and it has 10 times the intensity of the base level of human hearing? You with me?
Mm-hmm.
So if I do 10 times I naught here, over I naught, then what does beta 1 come out to?
1,000.
Just one.
Am I?
You guys are just spitting in the dark.
No. Log base 10 of 10 is 100 times 10 is 1,000, right?
Log base 10 of 10 is 1.
Oh.
Oh, it's 10.
10.
Yeah, because I forgot the first.
Okay, so it comes out 10.
Yeah, I lost.
Just
The I naughts cancel out.
Yes.
So we're doing log base 10 of 10.
10 to the power of what?
10 to the power of what gives you 10?
Oh.
1. 10 times 1?
Okay.
So when I increase by a factor, my intensity by a factor of 10, we now have 10 decibels, right?
Yes.
Is that pretty intense?
No.
Okay.
Beta 2, we'll say is 10 times log, and this time I'll increase that sound again by a factor of 10. So now we have 100 times I naught over I naught.
Oh, so that's 100.
What's log of 100?
10.
10 to the what equals 2? Or 10 to the what equals 100?
2.
2. 10 to the 2 equals 100. 10 times 2 is 20. So when I increase it by a factor of 10, my intensity by a factor of 10, my sound intensity only increases by 10. So sound intensity is increasing linearly as intensity is increasing exponentially.
What?
I made the number here 100 times bigger, or 10 times bigger, and it only made this number twice as big.
So if you were to do 1,000.
That is, yeah, so let's do it. Let's jump to the chase.
Okay.
B3 is equal to 10 times log, and this time we'll make it 1 million times, 10 to the 6. I naught over I naught. So I increase the intensity now 1,000,000-fold.
That's just 60.
Comes out 60. So taking our threshold of hearing, not threshold of hearing, that was this, but taking this, no, threshold of hearing, taking our, but then it doesn't multiply, so we'll say starting with this sound right here.
Okay.
When I took this sound, no, we'll still say this one. Sorry, I need nice fractions.
Okay.
When I took this sound right here, the intensity that produced this sound, so from 100 to 1,000,000, I increased it, the intensity 100,000 times.
Yes.
The waves I was using had 100,000 times as much power as the waves I was using here, when I went from here to here. And yet, it only produced a sound that was 3 times the sound intensity level. This only increased threefold. Going from here to here only increased by a factor of 3.
Yeah.
Yet going from here to here, we increased the actual intensity by 100,000.
How does that work though? That's like a lot of intensity.
A lot more intensity does not necessarily mean you hear it a lot more.
Yeah, but I mean it hits your eardrum. Where does the rest of the intensity go?
It goes into your eardrum and you hear it. But then there's some communication about how you hear that's just in your biology. You don't hear everything. There's some base level that you start to hear, right?
And then some max, I guess.
Well, and then it gets to the point where it can hurt. So we go all the way down here. By the time you get to 120 decibels, that's the threshold for pain. At 120 decibels, it starts to hurt
Because it's so loud.
because it's so loud. So here's where, so let me just read some common things for you. Threshold of hearing, 0 decibels. The rustle of leaves, 10 decibels. An average whisper, 20 decibels. Quiet radio in a home, 40 decibels. An automobile, 50 decibels. Ordinary conversation, 65 decibels. Busy street traffic, 70 decibels. An elevated train, 90 decibels. Threshold of pain, 120 decibels. Military jet aircraft 30 meters away, 140 decibels.
Wow.
So by the time you get to 120, we have an intensity equal to 1. This is 1 watt per meter squared. Threshold of hearing was 10 to the minus 12 watts per meter squared. So we increase this by 10 to the 12.
Holy cow. That's a lot of intensity, isn't it?
It's a huge order of magnitude change in the intensity. But I don't know what to say a lot of intensity is. 1 watt per meter squared is not that much.
It's not.
I mean, it's so loud that it hurts your ears, sure. But I mean, you could put headphones on and easily generate that much.
Yeah.
You could generate a watt per meter squared from headphones.
Yeah, because remember that intensity dies out the further out it goes. So I got some small power source, stick it really close to my ear, and I'll hear it really loud. Because intensity dies off fast.
Yeah.
Remember, whatever intensity I have right here, when it reaches Jeremy, by the time it reaches you, it's now 1/4 what it was. If I double the distance, you 1/4 the intensity.
Interesting.
And we covered that last time.
Yeah, we did.
Okay, so don't get confused. You're going to be asked to calculate intensity sometimes, and you're going to be asked to calculate sound intensity. This is sound intensity, this is intensity. Sound intensity is how humans hear, intensity is just the physics.
Okay.
Okay, don't want to get confused on those. Whew. Should we cut there and finish next time? We've covered the important stuff in the chapter that's going to cover your homework problems. Most of your homework. The rest of the stuff is just more interesting stuff now. Not a lot of math. Okay. So, move on to some of just the more interesting stuff now. Sugar. I don't want to redraw out this picture. Maybe let's do an example problem real quick with one of these. We'll just do the first one using that equation I just erased, but we'll rewrite that there. A 10-minute exposure to 120 decibel sound will temporarily shift your threshold of hearing at 1000 hertz from 0 decibels up to 28 decibels. Okay. 10 years of exposure to 92 decibel sounds will cause a permanent shift to 28 decibels. What sound intensity corresponds to 28 decibels and 92 decibels? So beta 1 is equal to 28 decibels. Beta 2 is equal to, was it 92 decibels?
Yeah.
And our job is to find the corresponding intensities that produce those decibels.
Okay.
You mean I and I naught?
The I's.
Just the I's.
I naught is a fixed number. I naught is always and forever 10 to the minus 12. That's the threshold of hearing. It's a
Okay.
constant. Okay. So now I need to find beta 1 and beta 2. So I know that beta 1, well, I know that beta is equal to 10 times log of I over I naught, like that, right?
Mm-hmm.
And I need to set this up as a function now in terms of I rather than beta,
How do you undo a log of it?
with an exponential. So, divide both sides I mean, we've solved a bunch of problems like this. I don't know why you guys are getting so lost. If I did something like y is equal to natural log of x,
Then you do
that's
it to
just
the
a
e.
log. Then you what?
Do it to the e.
Then you do it to the e.
Yeah.
So then you know that e to the y is equal to x. Same thing here. Raise it to the 10 instead of raising it to the e. Same exact thing.
Okay.
Okay. So first we'll get the log by itself. So beta over 10 now is equal to log base I, or of I over I naught. Raise both sides to the 10. So I get 10 to the beta over 10 is equal to I over I naught. Right? Didn't lose you in that step?
Nope.
Good. And then that gives us I is equal to I naught times 10 to the beta over 10. And if you're worried you'll forget that equation, you can just write it down. If you don't think you can write that.
Oh, so
But-
you just plug in B1
Right.
and B2.
Now you just plug in 28 and 92 and it spits it out for you. And I naught, don't forget, plug in I naught. And so if you do that, you should get 6.3 times 10 to the minus 10 and 1.6 times 10 to the minus 3. I don't see any point in actually plugging that in. Okay. So now, back to talking about pressure waves. And now we're going to talk about standing waves inside of pipes, talk more about instruments. And before I do this, let me reestablish some intuition writing these two things out again, because that's, once again, the hard part. So if we draw our position wave, and then that looks something like this. Might be terrible. But then if we draw this wave, it's going to look like this. No, we should have been curving back. Okay, like that for a pressure wave and our displacement wave.
Yes.
And they're not perfectly in sync, they're shifted like this. So, what's the best way to say this? You remember that, okay, so if we had some standing wave now, so some standing wave meaning it now has nodes. A standing wave would be like the wave you produce inside like a pipe. Okay. You produce some standing wave. Same way you produce a standing wave on a string, you can also produce a standing wave on a pipe. Right?
How would you do that though?
In a pipe, I mean.
What is a standing wave again?
It's a wave where so hard to do. I just want to show you. Let's see. So when I vibrate a guitar string, one of the ways a guitar string might vibrate looks like this.
Yeah.
And then this will shift down as this shifts up, and it will go like this. And this point will never move, and we call that point a node.
Okay.
And this point will never move, and this point will never move. Those were nodes, and these points we called antinodes.
Mm-hmm.
Okay, so now when I produce a standing wave with sound, it's going to produce a standing wave in terms of its displacement wave, and it's going to produce a standing wave in terms of its pressure wave.
Standing wave meaning it looks like.
It's going to look like this. There's going to be nodes and there's going to be points that just fluctuate up and down.
Yeah.
It's what happens when you send the wave down and it interferes and is able to bounce back somehow. And when you superimpose those onto each other, when you add those two waves onto each other, it came out to this perfect sine squared wave. And the sine squared wave had these node points. Right?
So how do you do that in a pipe then if it's not bouncing back?
For now, you can just think about it as capped at the end.
Okay.
For now, yeah, that's good enough. We're just trying to establish some intuition about how these two waves are related. So you have some standing wave inside of there. Now, maybe we should say this right now. I don't want you to get confused by standing wave in a pipe. You can produce a standing wave in a pipe without it being fixed at the other end like you have to have with a string. because it's the atoms themselves jiggling. And so I start the atoms here jiggling, 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 jiggling all the way down, and those jigglings sends back jigglings as well.
Okay.
And so you produce a standing wave in a pipe.
Oh, so it doesn't necessarily need to be kept.
No, it doesn't need to be kept.
Okay.
Okay. Anyways, so if this wave right here was our displacement wave, and let's pretend it's a standing wave,
Okay.
then this right here is what our pressure wave would look like as a standing wave.
Yes.
You with me so far?
That makes sense.
Here's what's to notice. Here's the nodes of our pressure wave, or of our displacement wave. Node, node, node. Here's its antinode. And here's its antinode. Oops. Not there. Here's its antinode, here's its antinode, and here's an antinode. For our standing wave, right?
Mm-hmm.
The nodes are where it doesn't move. The antinodes are where it moves the most. I didn't mean to put that there. So it moves the most here, and it moves the most here. The thing to notice is that nodes of our position wave are antinodes of our pressure wave.
Yeah, I see.
And nodes of our pressure wave are antinodes of our position wave.
Okay.
That's the important relationship you need to get from that picture. And the author has a much better picture on page 523, trying to make this make nice intuitive sense to you, showing you with time how they model out. I just don't want to draw something that complicated
Yeah.
and walk you through the picture. That'd take forever. Okay. So nodes and antinodes differ in that way. So now when we have some standing wave inside of some pipe, start by thinking about an open pipe. So I've got some piece of pipe here, and it's open at both ends. And it can be open at both ends like that, or it can be kind of what you see on instruments is just a small hole on one end, and then completely open on the other end. Doesn't matter. Open pipe, doesn't matter how it's actually drawn at the end. The point is open here, open here.
Okay.
Now, since it's open here and open here, you can't get any pressure fluctuations there. I can't get pressure fluctuations at the end of a pipe.
What do you mean by a pressure fluctuation?
The pressure at the end of the pipe pretty much stays the same as the atmospheric pressure outside. Think about it as water for a second. I can't have an open pipe and produce high pressure in that pipe at the same time,
Yeah.
since it's open to the air around it. So it's much harder to compress. It is possible to compress. It's much harder to compress compared to the air inside of here. Right?
Mm-hmm.
And so with pressure waves, if we were talking about pressure waves inside of here, then the pressure wave here always has to be a node pressure wave. The node always has to be at the ends. So one possible pressure wave I can do here, maybe I'll draw it at the bottom. I could have a pressure wave that looks like, for example, here, this. That's a pressure wave I could put inside that pipe for a sound wave.
Okay.
One wavelength. I drew that terrible, but I think you get the idea. Let's see how he draws them. Oh, he draws them top and bottom. That kind of makes it nicer, doesn't it? So you can draw something like, or like this.
Oh, so it's like half a wavelength?
So half a wavelength is exactly right. So a pipe that is open at both ends, then the max wavelength I can fit in there is, let's say this pipe is length L, then the biggest wave I can produce inside of there and have it be a standing wave is where lambda is equal to 2L, because it has to be half a wavelength, right?
Mm-hmm.
Or, if we write that as a frequency, remember that velocity is frequency times lambda. Did I do that right?
Yes.
Then, writing this in terms of its frequency, so this is the biggest one, so we'll call that lambda 1. We can fit tons of waves in here. This is the biggest one we could possibly fit. So F1 then, let's solve this really quick. So lambda then is equal to V over F.
Okay.
Did I do that right?
Yeah.
So over here,
if we replace that, then I know that V over F1 is equal to 2L, or in other words, I know that F1 is equal to 2L V over 2L, right?
Yes.
Now, that's just the biggest wavelength I could fit in there. I could also fit a wave in there that looks something like, let's see if I make a nightmare of this. Maybe I'll just try and draw over it. I'm going to try and fit a whole one in there. Something that goes like this. Maybe something like that. So more than the whole one. Let's just draw a completely separate picture. It's easier to draw the wave than the pipe. Okay, if I have one that looks like this. And then one that looks like this. Okay, now here's my pipe length L. With me?
Yes.
So there's another possible standing wave I can fit in there. Remember, these are pressure waves, so the pressure here and here is 0 nodes. And in that case, then now lambda 2 is equal to 2L. Or in other words, if I solve for F2 here, F2, then what would I
Lambda
get?
2 is equal to 2L.
Oh, sorry. Lambda 2 is just equal to now L.
Yeah.
Right? Because one wavelength is the whole thing. And now frequency is V over L. And another way I can write lambda 2 is it is also equal to lambda 1 over 2. And another way I could write this is equal to 2 times F1.
Okay.
Right?
Yes.
Now I could have fit another half a wavelength in there, so I could compress this again and fit another half, because then it would still end open like that. And another half, and another half, and another half. And I can put as many half wavelengths in there as I want and compress the sound. And it will still work.
Okay.
So in general, anything of the form lambda equal to L over 2N works. Which is the same thing as Y1 over N. Or lambda 1 over N. I can fit anything of that wavelength in there, or writing it in terms of our frequency, any frequency, we'll call that lambda sub n, f of n equal to V over L n times V over L, or in other words, V over 2L, I mean, right?
2L, 1, 2. Oh, I see it.
Or in other words, n times F1. And we had those exact same equations when we were talking about vibrations on a guitar string.
Yes.
So blowing through this pipe, when I blow through this pipe, the sounds, the possible sound waves that will create these standing waves will be either F1 or some multiple of F1. Only those frequencies will create standing waves inside that pipe.
Yes, but these standing waves are different, right? With a guitar string, it's your position, but with the pipe, it's pressure, right?
This was with the pressure waves. I could have also drawn the position waves.
And they do the same thing?
It's just the position wave, you draw it kind of funny here, because I'm not sure how to draw it. Because remember that a position wave now
It's just shifted, right?
has to be, since these are nodes for a pressure wave. Did I draw that right? I drew the position wave.
That's the position wave?
Yes. Because here's equilibrium for pressure. Or here's equilibrium, sorry. The pressure wave would look like this. Let's try and draw the same thing for a pressure wave now. Because the pressure wave would start at 0, and then it would go up and then down, something like that.
You could just.
No, it
draw
needs to get back to 0.
Yeah.
So the pressure wave would have to look something like this. Because it has to be 0 at the ends.
Doesn't that look like a guitar string though?
Yeah, it also looks the same as this thing if we draw the other pressure wave, because the other pressure wave coming back could be something like this.
Oh, I see it. Okay.
So that just shifted.
Yeah.
So the pressure wave has to be 0 at the ends, because those are open to the atmosphere.
But okay.
Okay. So pressure wave, amplitude wave. So we drew the displacement, or the amplitude wave. Displacement, I should probably call it. Displacement wave.
Okay.
Okay? So the standing waves that we can get to fit in here are waves that look like this, have frequencies like this. You with me?
Yes.
So now what about if we close off the end of the pipe? So we blow into a closed pipe now. So the pipe goes down and then it's actually blocked at the end like that.
Wouldn't it just bounce back then?
It would bounce back, but what kind of waves can we put in something like this? Now notice that the air at the end of the pipe can't shift. It can't move back and forth
Yes.
because it's blocked.
That's right.
So if we're drawing our displacement wave now, then right here it has to start in the middle. It can't move up and down. So it has to look, we could have one that looks like this. So you could blow into a container like that and get a standing wave.
Oh, and that's the max one.
Which in that case, lambda 1 is equal to L over 4, or 4L I mean, because we only have 1/4 the wave there now, right?
Yes.
And F1 is equal to V over 4L, right?
Yeah.
Because it's still open on this end, so we have to have a pressure node here, or in other words, a displacement antinode here. So it has to be open like that at this end, but it has to be closed at that end. I could have also had a wave that looks like this. I'm just going to make the container bigger so I can keep drawing the same waves. It could have also come like this. And then this one could have come up like that, right?
Mm-hmm.
Which in that case, lambda 2 is equal to, now if this is our L, lambda 2 is 3/4 that. Is that right? 4/3 the length.
Wait.
4/3 the length.
4/3?
Yeah, because it's a little bit more than this. This is 3/4 of the wavelength. The wave isn't finished yet. The wave needs to go, like that. It needs to get back to there to finish.
Yeah, I get that. So wouldn't it be?
So this is
3/4?
3/4. L is equal to 3/4 the wavelength.
Yes.
Or the wavelength is equal to 4/3 L.
Oh, I see.
Okay, so lambda 2 is equal to 4L over 3. With me?
Mm-hmm.
And frequency 2 is equal to 3V over 4L.
Yeah, I see.
And we could have extended it further, and we could have had this now come like that, and this now come like that, and that would have made lambda 3 equal to 4L now over 5, and F sub 3 would now equal 5V over 4L.
Okay.
Okay, so notice with the frequencies, we're increasing now by odd numbers. It was 1 times that, then 3 times that, then 5 times that. So F sub n in this case, is equal to 2n plus 1, the next odd number, times our initial frequency, our base frequency, F1.
Gotcha.
So instead of just n, it's 2n plus 1. It's only the odds. Similarly, lambda at n is equal to lambda 1
divided by 2n plus 1. And that's what it is for a closed pipe.
Just closed at one end though.
Close at one end. Yep. Open at both ends and then close at one end.
What would happen if they were both closed at one end? And they were able
How
to
do you
make-
create pressure differences in there now?
Oh, I see.
So with musical instruments, these are the two different ones that we have.
So this is how musical instruments work?
Uh-huh.
You close it and then open it to get different frequencies?
Not really. So think about something like blowing a recorder. Blowing a recorder, what do you have? You have a bunch of finger holes at the top. So here's the part where you're blowing in, and then you have a hole there, hole there, hole there, whatever. Here's your recorder, and it could be open at that end, and then here's the end that you blow in, right? And you blow right here.
Mm-hmm.
So when you put your fingers on a recorder, if you don't put your fingers anywhere, then notice that it's open here.
Yeah.
Yes.
And so the longest wavelength you could possibly have is one that looks like this. I'm terrible at this. That's the longest wavelength you could possibly fit there. You can fit that or shorter.
Yes.
Now notice if you put your finger on this hole, and you put your finger on this hole, and you put your finger on this hole, now the minimum wavelength you could possibly produce blowing in here is this thing. Not going to do a very good job drawing it, but you see a much bigger wave. And so when you're blowing in a recorder, if you don't put your fingers on any of the holes and you blow, it gives you a high frequency sound. If you cover them all, then it gives you a lower frequency sound.
That's
Because
pretty
it has
cool.
higher and lower wavelengths.
Yeah.
And so manipulating those lengths is ultimately what produces those higher and lower sounds. So the longer the pipe, the lower the sound. And all those holes do is change the effective length of the pipe.
Yeah, that makes sense.
Okay. So maybe we'll call it there for now. I don't know. The last thing we really have to talk about is the Doppler effect.
The Doppler effect.
Yeah. I don't know. Should we just do it now? Or do you want to do homework problems?
Well, I mean, if we have time tomorrow, we can just do homework tomorrow.
Okay, we'll try and just finish this out. So, well, we also need to talk about interference and the Doppler effect. Interference you can now pretty much understand with these pictures. So to add sounds together, or when I produce two waves in the same location, then those waves just add together, right?
Yes.
So imagine I'm talking and I'm producing this sound wave. Here's the sound wave I'm producing.
Okay.
Now imagine that you're talking and you're producing the exact same sound wave that I am. But you step backwards half a wavelength. So let's draw this actually on a coordinate system so that we can draw them both. And we'll have you step forward and step back so that we can fit it on here. So here's me talking, and for some reason I'm talking with a perfect frequency of just one tone. Got him kind of fatter, but oh well, you get the picture. Now imagine that you step forward in front of me, exactly half a wavelength.
Okay.
So you're standing right here. Here's half a wavelength, so you're standing right here, right? Here's you, and you start talking with the exact same frequency now that I am, and you produce the exact same wave.
Okay.
So then your wave looks like this. Right?
And they cancel each other out.
When you add those two together, they perfectly cancel each other out. And we call that destructive interference. So two waves that interact with each other to the point where they perfectly cancel out, we call that destructive interference. Now notice that you didn't have to just be half a wavelength ahead of me, right? You could have also been right here and start talking.
Okay.
Or right here. So if you are a half a wavelength off from me, or some number of half, or some whole number, how can I say this right? If you are this many wavelengths ahead of me, so take the wavelength over 2, plus any number of wavelengths. If you are offset by this much from me, so plus n wavelengths for any integer n.
Okay.
If you are offset this amount from me, whether you're just a half off, or you're a half plus a whole wavelength off, or a half plus 2 whole wavelengths off, then you and I now have destructive interference. And if I spoke perfectly this one pitch, and you spoke perfectly that one pitch, and we offset from each other exactly pi halves, then we would perfectly cancel out each other's sounds.
Is it possible to do this?
It's possible to do close to this. You could have a microphone measuring sounds coming from certain places, have 2 speakers play a perfect sinusoidal wave, and find places where the sound basically goes away and then where it gets really loud. Because now notice that if you were standing right here, or you were standing right here, or you were standing right here, and you started talking, now your wave and my wave perfectly coincide.
And
so it adds to it, and that's constructive interference. And so constructive interference happens if you're offset me by just n wavelengths. So if you're offset to me by just n wavelengths, then we have constructive interference. If you're offset to me by a half and then some number of wavelengths, we have destructive interference.
That makes sense.
Okay, so that's interference versus interference. Beats is like a 1-page section. We're not going to do anything with beats, but you can read about beats if you want.
Beats.
Beats, as in
Oh,
a beat, not Dwight Schrute. Okay, and so now the last thing we need to talk about is the Doppler effect. And the Doppler effect has to do with the fact that sound travels through air at the same speed no matter what. And it doesn't matter how fast I'm moving. If I'm the source of the sound, so I'm screaming, it doesn't matter how fast I run, it doesn't make the sound travel faster. Right? If I shoot a gun straight up in the air and the sound of the bullet travels towards you, and then I drive a car by and the instant I'm right here, I shoot the gun up to the air and the sound travels towards you, both those sound waves travel towards you at the same rate. Doesn't matter how I'm moving, sound travels how sound travels.
Okay.
Does that make sense?
Yeah.
So the Doppler effect is related to that. It's based on the idea that sound travels through air at a constant rate, 344 meters per second. And so what that ends up happening is, if while I'm coming towards you and I talk, even though the sound doesn't get to you any faster, the frequency goes up. And if I walk away from you while I talk, even though the sound doesn't come at you any slower, the frequency goes down. And that change in frequencies, based off of how you're moving, is what we call the Doppler effect. So let's draw a picture, and then we'll do some math. So here's some source, and it's letting out sound. So it's letting out sound waves. And here's some listener, so we'll do S for source, and then here's some listener. And those sound waves travel to the listener. Now, let's see, which one does the author do first? Because we want to start with the simple case. So we'll start with the simple case where the source of the sound isn't moving, but you, the listener, are moving, and we'll pretend you're moving towards the sound. I'll draw it in the picture, but it really doesn't matter if you're moving to or away from the sound. The masking came out the same. And does the author use V for your speed? He uses V for the speed of sound, so we'll use V for the velocity of the listener. V sub L for the velocity of the listener. So you're moving at S with some speed V sub L.
Okay.
Okay. So, what's the best way to say this? Here's the base equation that we're using, first off. So we know that velocity is equal to frequency times wavelength, right?
Yeah.
So if you are moving towards the sound wave for a second, then the sound wave moves through air at the rate that the sound wave moves through air. So this wave right here is moving towards you at v, right?
And we know that.
Yeah. Speed of sound, 344 meters per second. So let's first start with a physical example to help this make sense. Imagine that I'm in the back of a car, I'm in the back of a truck with Jeremy, and while Jeremy and I are in the back of the truck, I throw this marker at him at 10 meters per second or whatever, and it hits him, right?
Mm-hmm.
Now imagine that you are a pedestrian walking on the street. And instead of throwing it at Jeremy, while our car is driving past you at 100 miles per hour, I throw the marker at you, from my perspective at 10 meters per second.
It's going to hit me at 110 meters per second.
It's going to hit you a lot harder than it would have hit him in the back of the truck. Because relative to you, the marker is going 110 meters per second.
Yes.
Right?
Mm-hmm.
Okay, similar concept going on here. You're the listener, you're walking towards the sound wave with some speed v sub L. The sound wave is moving relative to some stationary observer watching this all, this way at some velocity v. So the speed of the sound wave relative to you is v sub L plus v.
Can you say that again?
You are, so here's a stationary observer.
Yes.
Here's me. I see you walking this way with some speed v sub L. I see the sound wave traveling towards you towards v, at some speed v.
Okay.
What speed do you see the sound wave coming at you with?
Just v.
No, v plus v sub L.
Oh, yeah.
The sum of them. Okay, so the velocity that you see the sound wave coming at you with is v sub L plus v, right?
Yes.
And so that has to equal the frequency times the wavelength from your perspective.
Yes.
Okay, so just depending on what the wavelength is here, will determine the frequency that you see. How do I want to say that? So, yeah, we can keep messing with this. For your frequency, the frequency the listener hears. So the frequency the listener hears is equal to v sub L plus v divided by the wavelength. The wavelength, this distance right here. Lambda.
Okay.
Now, lambda there, we can use this equation now for the source. We also know that the velocity of the wave is equal to the frequency of the source times the wavelength that the source measures. We'll have the same wavelength in both these pictures. So that is also v divided by the frequency of the source. You with me there?
Mm-hmm.
I didn't solve that right. I just wrote equals, sorry. So lambda, I meant to write lambda equals. Lambda equals velocity divided by the frequency of the source. So, lambda we can replace here with the velocity of the speed of sound divided by the frequency of the source. With me so far?
Yes.
So now f sub L, the frequency of the listener, is equal to, when you divide, you multiply by the reciprocal. So we have v sub L plus v. I'm going to write my f of s first. V sub L over v sub L plus v all over v like that. You good with that?
Mm-hmm.
Which is equal to, just the way it's commonly written, f sub s times, I'm going to put the v's, I'm going to write those as separate fractions and write the v over v first. That was a v sub L. Now let's keep working like these. Okay. So this is the frequency that the listener hears.
Okay.
compared to the frequency that the source hears.
What's the
So the-
frequency of the source hears?
The source is a person emitting the sound. So you could be in a car, you're sitting there in a car listening to the stereo. You hear the music at some frequency at the source.
Mhm.
Jeremy's walking to your car at some velocity VL. What frequency does he hear compared to you? Here's the frequency you hear. The frequency he hears is the same thing as the frequency you hear, plus his velocity over the speed of sound. Notice that if he's not moving, if his velocity were 0, then v sub L is 0. So we have 1 plus 0 is just 1, so it's just f of s. So if he's not moving, he hears the same frequency as you.
Okay, but if he's moving pretty fast,
If he's walking toward you, then you have 1 plus some positive number,
yes.
which is going to be something bigger than 1.
Mm-hmm.
So he's going to hear the frequency you hear times a number bigger than 1, which means he's going to hear a higher frequency. If he were walking away from you, so his speed here was negative, then you have 1 minus some number,
Oh, which makes it smaller than 1.
which makes it smaller than 1, so he hears a smaller frequency.
Okay.
Now, notice what happens if he's running away from you at something absurdly big. What if he's running away from you at 2 times the speed of sound? That's how fast he's running away.
Then you hear a negative 1 frequency.
Which doesn't make sense,
Yes.
because you won't hear anything. Because you're running away faster than the sound can get to you.
Oh, got it. Okay.
So, kind of breaks down in negative numbers. So as long as he's moving at speeds slower than the speed of sound, or at least not running away from you, he can run towards you at the speed of sound and hear double the frequency. That's perfectly fine. But if he runs away from you, he won't hear any frequency, and so the equation kind of breaks down.
I see.
Okay, so that was just with one moving sound. Now let's say we have 2 moving sources. Let's say now that you're both moving.
Oh, so the source and the listener?
Yes. So that was just a special case to help us get comfortable with what's going on. So try and draw an accurate picture for how the sounds will look as you drive along. So here's more like what it's going to look like, assuming the source is moving this way. Then the sound waves are going to look more like this, with this being the source. And let me try and get intuition for why they're offset like that. Or does it already appeal to your intuition?
It's just moving that way.
Yeah.
Yeah, the source was right here when it emitted this sound wave. It was right here when it emitted this sound wave, and now it was right here when it emits this sound wave.
Yeah.
And so it's moving that way as it emits the sound wave, so the sound waves are spread out like that.
Yeah.
Perfect. So, good so far. So, here's our source, and we still have our listener moving this way. Here's our listener, and we also have our source moving with V sub S, and this is moving that way with V sub L. Okay, so we still know that the frequency the listener hears, is that how we're going to be ultimately writing this? Yes. We still know that the frequency the listener hears is going to be equal to, from this equation, it's going to be equal to the velocity relative to the frequencer, relative to the listener. Let's start with that really quick. What velocity now are the waves coming at the listener? What's the speed of the waves now?
The speed of sound
yeah,
plus the
speed of sound.
velocity of the listener minus the velocity.
The sound still travels through air at the speed of sound.
Mm-hmm.
That doesn't change. So it's still, let me make sure you understand this. The speed that this wave is coming at this person is still just v plus v sub L. That's how fast this wave is traveling towards a person. It doesn't matter that the source is moving, the speed of sound is still the speed of sound.
Yes.
Okay, so frequency is going to be velocity divided by, now lambda here is what's going to be weird. So we're going to say lambda in the back. So lambda now is this wavelength right here. And we'll say y sub b, lambda sub b, so that we don't get confused. Think it's the same thing as before.
Okay.
lambda sub b. Now for the source, still using this. For the source, we have v is equal to the frequency of the source. How's the best way to say this? The lambda here, okay, that's a distance. We can think about that as a distance. That's this distance. And that's going to be the speed of sound plus the speed that the source is moving that way with. So it's going to be v plus v sub s times the time.
The time that they were moving?
Times the time, how can I say this? Here's where we're going. F sub s. And instead of thinking about it that way, we can think about it as lambda here in the back is equal to v plus v sub s times the period of this wave coming from the source. So the time that it takes in between these waves to emit a wave pulse.
Okay.
That's our period, right?
Yes.
And so we're going to divide by that period gives us our distance. Or we're going to multiply by that period to get our distance. Take a velocity, multiply that period, it gives you your distance.
Yes.
Okay, that's what we have here.
Why is it a plus vs?
Because from the back,
Oh yeah, from the back.
because those are the waves taking in, right?
So why are you dividing by the frequency of s?
Because I'm multiplying by the period.
Ah, duh.
Okay, that's probably the best way to make that make sense. So if you plug that in now here, then we get that the frequency heard by the listener is equal to the velocity divided by the wavelength, which is going to be v plus v over s, all times f of s, f sub s. Bless you.
So that's just f of s over... Oh, that is what it is.
That is what it is.
Yeah. Okay.
So now notice two things here. Notice that the faster you move, the higher the frequency you hear, and the faster the source moves, the lower the frequency you hear.
That makes sense.
Which makes perfect sense.
Okay.
Good?
Yep.
And that's what we call the Doppler effect. Okay. And then, unfortunately, we won't talk about shock waves, but I at least want you to understand what a shock wave is. A shock wave is what happens when the source now is traveling faster than the speed of sound. And you get shock waves from things like
An earthquake?
you get it like from a jet. When a jet travels faster than the speed of sound, it produces a shock wave.
Oh. Yes.
So what happens when, so our jet's right here and it produces some sound, right?
Mm-hmm.
And it produces some sound like that. It produces some sound that over 3 seconds, that sound wave gets this far. And then the jet moves here, and over 3 seconds, that sound wave moves, well, the jet gets here, and over 3 seconds, the sound wave moves this far. And then the jet gets here, and over 2 seconds, it gets that far. So here's the jet, in 3 seconds, that sound wave gets right here. After 1 second, here's the jet, in 2 seconds, the sound wave gets right here. After 2 seconds, here's the jet, and in 1 second, the sound wave gets right here. And the sound waves keep getting further and further ahead of each other.
Yes.
So this was the first sound he emitted, this was the second sound, this was the third sound.
Okay.
And so notice that the third sound is ahead of the second sound, is ahead of the first sound. Not like what we had here.
So it's breaking the sound barrier?
Yeah, breaking the sound barrier. And so this is what we mean by a shock wave, when you have this kind of phenomenon going on.
That makes
So-
sense.
thought experiment that's beyond impossible, but just to give you intuition for what I'm saying here. Imagine there's a jet traveling faster than the speed of sound. Now inside that jet, a guy shoots a gun, kills a girl, the girl screams, right? Now that jet comes past you, and you can hear all that as it comes by because the jet carries the sound. You would first hear the girl scream and then hear the gun shot.
What? How?
Because you'd hear the second sound before you hear the first sound.
That's so weird.
Okay?
Yeah.
Beyond impossible, what I just said, but gives you good intuition for what we're talking about with this sound, with this shockwave. It is weird. Here was the first sound emitted, here was the second sound emitted, here was the third sound emitted.
So the sounds we hear from a jet, we hear the last sound it makes.
Well, the sound is so covered in everything that, forget it, you're not going to be able to discern anything. It's just,
Yeah.
shockwaves are just destroying sound, but I just want you to get intuition for the weirdness of what's going on. The first sound wave is getting to you before the second sound wave is getting to you before the third. Or, I said that backwards. The third sound wave gets to you before the second sound wave before the first. And so you're hearing sound in reverse order, if you want to think about it that way.
Okay.
Okay? So that's what shockwave is. And there's just one simple equation in there, but I wanted you to know about shockwaves. Okay, so that's it for sound, and then we'll use the rest of the class to talk about problems. We can do more example problems or homework problems or whatever you want, or go over the test.